In this video, we are going to have a short tutorial on chemical kinetics, which is the branch of physical chemistry that studies the rate of a chemical reaction. Don't forget to like and subscribe the channel after watching, so that you keep in touch with every update from this channel. So for the outline of this video, we're going to look at the rate of a chemical reaction, the rate law equation of a chemical reaction. We will look at the effect of catalyst on a chemical reaction. We'll look at activation energy of a chemical reaction and also discuss the energy profile diagram of a chemical reaction. So what is the reaction rate or the rate of a chemical reaction? So reaction rate or the rate of a chemical reaction is the change in the concentration of a reactant or product with respect to time. Let's take this schematic reaction in which A is being converted to B. Now in this reaction, the A is the reactant, whereas the B is the product. The rate can be expressed in terms of either the reactant or the product. So the time duration for the disappearance of the A to form the B, or the appearance of the B from A, is what we define as the rate of the reaction. Mathematically, rate can be expressed as the change in the reactant concentration with time, or the change in the product concentration with time. Now the change here simply means that the final amount left minus the initial amount. For a reactant, since the final amount is going to be less than the initial amount, their difference is going to be a negative value. But the rate of a chemical reaction is always a positive magnitude. Therefore, we have to bring in a negative sign so that it can cancel out that negative value to get a positive value for the rate. Unlike that of the product, where the final product is going to be, final amount is going to be more than the initial amount, and their difference is going to yield a positive value. Let's take this sample reaction and see how we can derive the rate of the reaction from the individual species. We have A plus 3 moles of B giving you 2 moles of C. The 3 and the 2 are the stoichiometric coefficient of these two species. So the rate is measured as the disappearance of the starting material, which is either the A or the B, or the appearance of the product, which is C. So as we said earlier, the rate can be expressed as the change in the concentration of A with time, the change in that of B with time, or the change in that of C with time. If it is always the reactant, then have to introduce a negative sign to show the decrease in the concentration. Now, if the species has a coefficient, the rate is always expressed as the reciprocal of that coefficient. So here, if it is 3 moles of B, then the rate is going to be 1/3 times the rate of the B. If you have 2 moles of C, then the rate is going to be 1/2, which is half of the rate of the C with respect to the product. So generally, the rate of a reaction is the change in the concentration of the reactant or product in a given time, as shown here. So if you have the change in the concentration of a reactant or product with time, then we tend to define what a rate is. Let's see how we can derive the unit of the rate of a chemical reaction. Concentration is measured in mole per dm cube, or mole per liter, or molar, whereas time is measured in seconds. So the unit of rate is going to be mole dm cube minus dm cube s minus 1. So this one be the numerator, which is the concentration, then the s is the denominator, which is the time. Now the square bracket here in kinetics just represents concentration. So this one also has the unit of mole per dm cube because it represents concentration of a reactant or a product. Now let's come to the rate law of a chemical reaction. Now what does the rate law state in a chemical reaction? When we say rate law, then it is allowed states that the rate of a chemical reaction is proportional to the reactant concentration. So how fast or slow a reaction can proceed depends on how much of the reactant was used initially. So we have A plus B giving you C. The rate law equation says that the rate of this reaction is proportional to the concentration of the reactant, which is A and B. Now in this reaction, the K here is what we call the rate constant of the reaction. The R is the rate of the reaction. The X and the Y are what you call the reaction orders. Then the A and the B are the concentrations or the compounds. The X and Y are called reaction orders, and they are just degrees or parameters that defines how much the rate depends on the concentration of the individual reactant. Let's have this general reaction in which A plus B gives us a particular product. Now the rate law of this reaction says that the rate is proportional to the concentration of the A and that of the B, because the A and the B are the reactant in this reaction. The K, X, and Y are all values which can be determined by experiment. So the X and Y are normally small integers. As we said earlier, they are called the orders of the reaction, and they are just small integers, which defines how much the rate depends on the reactant concentration. So the X is the order of the reaction with respect to the A, this one. Then the Y is the order of the reaction with respect to the B. If X is equal to 1, we say the reaction is in the first order with respect to A. If X is equal to 2, we say the reaction is in second order with respect to A. And if X is equal to 0, we say the reaction is in zeroth order with respect to A. The same thing applies for the B. So if, for example, if you say X is equal to 2, this parameter just defines the dependency of the rate on the reactant concentration. If X is equal to 1, then it means that the rate increases linearly with the reactant concentration. So when you increase the reactant concentration by a particular parameter, the rate also increases by the same parameter. If the B or the Y is also equal to 1, then we mean that that reaction is in first order with respect to the B. So when you increase the B by a particular figure, the rate also increases by the same figure. But when we say if X is, let's say, equal to 2, it means the reaction is in second order with respect to A. If, let's say, Y is also equal to 2, then we say that the reaction is in second order with respect to B. Now, if we say X is true, then it means that when you increase the concentration of the A by a particular figure, the rate also increases by the same figure squared. Let's say if the X is true, we say the reaction is in second order, then it means that when you increase the concentration of the A by, let's say, 2, the rate also increases by 2 squared. That is to say, generally, for every reaction in second order, when you increase the concentration by a particular figure, the rate also increases by the same figure squared. Look at this. Let's say the X is true. such that the reaction is in second order with respect to A. Then when we double A, the rate is going to increase by the 2 or the double squared, which is 4 times. When we increase the A by 2, the rate will increase by 2 squared, which is 4. In the same way, when we increase the rate by 3, which is we triple it, the rate will increase by the 3 squared, which is what? 9. Let's take it again. If let's say the x is 2 and that this reaction is in second order with respect to A, when you increase the concentration of A by 2, the rate also increased by the same 2 squared. When you increase the concentration of A by 3, the rate also increased by 3 squared. So by figure, if you see, if you double A, then the rate will increase by 3 to 4 times. This 4 times means that double to power 2 because the x is 2. When you triple A, then the rate increased by 9. This 9 means that triple to power 2 because the x is 2 or the A is in second order with respect to the reaction. Now, the overall rate or order of this reaction is by adding the orders of the A and the B, X and Y. So let's say the X is 2 and the Y is 3. Then the overall order of this reaction is 2 plus 3. Let's say 2 plus, which is 5. So by expression, the overall order of a reaction is given by X plus Y. If let's say X is 1 and Y is also 1, then the order of this reaction becomes 2 because it's going to be 1 plus 1. Let's see how we derive the unit of the rate constant as we defined here. If you want the unit of this K, you have to make the K the subject of this equation. So just divide both sides by the concentration of the A and that of the B. So you get the rate to be equal to, the constant to be equal to the rate over the concentrations of the A and that of the B. Simplifying, the rate is equivalent to concentration over time. Then these are the concentrations with their respective orders. The N represents the overall order of this reaction. When we simplify this, then the unit of the rate constant for every reaction in a particular order is given by this expression, where the N represents the order of the reaction. So if N is 1, just put in here. You're going to get 1 minus 1, which is 0 here for the mole, 1 minus 1, which is 0 here for the L, then x to the power negative. It means that for first order reaction, you're going to get the unit of the K to be x to the power minus 1. This formula is used for finding the unit of the rate constant for every order of a reaction. Let's have this. For a zeroth order reaction, the unit of K becomes this when you use this formula. For first order reaction, this becomes the unit of K. For second order reaction, this becomes the unit of K, and this one too for third order reaction. So shown here are some chemical equations and how you can express their rate laws with their derived orders. You can go through them to understand. Let's come to factors affecting the rate of a chemical reaction. Let's say you have an atom A plus an atom B giving you atom or a molecule C. This is a chemical reaction, and series of events goes in before the A and the B can be converted to C. The following event must occur before this reaction can proceed. Before you can convert the A and the B to C, there must be a collision between A and the B. So the molecules of A and the B must collide with each other to give what you call the C. Now the collision must be big enough to produce an energy which can overcome what you call an activation energy, which we are going to discuss in the next few slides. Then the reactant must form new bonds to produce product. So we have this reaction. There must be a collision between this reaction, and that collision must produce an energy which can overcome the energy barrier we call the activation energy of this reaction. Then bonds must be broken in the A and the B. Then new bonds must be formed in the A and the B to form the C. That's how basically reaction occurs. Now let's see factors that affect these three parameters. These three factors, or what affects these three parameters. Factors affecting the rate of a chemical reaction. We have concentration, temperature, nature of reactant, catalyst, and also surface area. For every reaction, if you have more concentration of the reactant, then the reaction can proceed easily. So when you increase the concentration of the reactant, the rate of the reaction increases because more of the reactant become available for the reaction to occur. When there is an increased temperature in a chemical reaction, there is going to be rapid bond breaking, rapid collision, which is from the increased kinetic energy of the molecules which are involved in the reaction. So temperature basically also increases the rate of a chemical reaction by increasing molecular kinetic energy and also collision, which result in bond breaking and new bond formation to produce the product. We also have nature of a reactant. Now the reactant can either be a solid, liquid, or a gas. For every reaction, all molecules must be in their gaseous state before they can proceed. If it is in a solid state, it will change to liquid, then to gas before it can proceed. If it is in liquid state, it must change to gas before it can proceed. This means that if you have an atom in a gaseous state, its rate of a reaction is going to be very fast as compared to that in a solid state. Also, the sizes of the molecules counts here in the nature of the reaction. If the atoms involved in the reaction are very small, they can easily bond breaking to form new bonds for the product to be formed. Catalysts are basically substances which increase the rate of a chemical reaction, but they don't undergo any degradation at the end. We are going to look at them. And also surface area of the reactant. If the surface area is more exposed, more energy can be absorbed to break the bonds, which can increase the rate of the reaction. Let's come to the effect of catalyst, as we said earlier, on a chemical reaction. So a catalyst is a substance which is added to a reaction to increase the reaction rate without themselves being consumed in the reaction. For example, when you take organic synthesis, you can have palladium, PT, which are all used as catalysts in organic synthesis. These are all heavy metals which are used in organic synthesis, and also enzymes in biological systems which act as catalysts to speed up biochemical reactions. PD, PT, and enzymes are all examples of catalysts which speed up reactions. How do they increase the rate of a chemical reaction? They do so by decreasing the activation energy of the reaction. Then what is an activation energy? So activation energy is the minimum amount of energy which a species must attain in order to undergo a specific reaction. So as we discussed earlier here, if you want to convert the A and B to C, there must be bond breaking and new bond formation. And this new bond formation, or the bond breaking, is achieved by absorbing some amount of energy to break the bonds to form the new one. Now, the minimum amount of energy that can be attained for these bonds breaking to form the product are what we call the activation energy. So, as we define here, it is the minimum quantity of energy that a species must attain in order to undergo a specific reaction. Let's have this schematic representation of a catalyst. Let's say this and this are the reactant. The two are the reactant. Now, catalysts just convert the reactant to the product without themselves being consumed at the end of the reaction. They just speed up the reaction and go back again to pick up the next reactant and convert them back to the product. So catalysts are not affected in the reaction, but they just speed up the reaction by just lowering the activation energy of the reaction. So let's have this energy profile diagram, which is just a bioenergetic or the energetics of a chemical reaction, which involves the plot of the free energy in the system against the reaction, the progress of the reaction. So this is the free energy which can be used to speed up the chemical reaction and the progress of the reaction. This is substrate or the reactant, and this is the product. The vertical axis is the energy magnitude in the system, as we said. This one is the rate of the reaction. The delta G plus is what we call the activation energy of the reaction. Then the delta G is the free energy of the reaction. Now, for every reaction, for this substrate to be converted to the product, it must attain some amount of energy for the bonds to be broken so that we can form new bonds in order to get the product. For every reaction, a substrate will attain some amount of energy and increase in energy content gradually. So it gets to a point where it can easily convert the reactant to the product. Now, the point where the reactant can easily be converted to product, which is this point, is what we call the transition state. And the atoms or the species found at this point are what we call the activated complex. So the activated complex are easily converted to the product because they are energized. They contain some amount of energy which can easily be used to break the bonds to convert them to the product. The difference between the energy system of the reactant or substrate and the activated complex is what we call the activation energy. The transition state difference and the substrate or the reactant energy difference is what we call the activation energy. So take this reaction. The product always has a decreased energy system as shown here, because in any chemical reaction there is some loss of energy as heat. So those energy lost as heat are what is represented here called the free energy of the reaction. If there's a reaction, what catalysts do is they just decrease the energy content or the activation energy of this reaction. So if you have this as activation energy 1 and activation energy 2, this one is the uncatalyzed reaction because it has no catalyst, so it has a very large activation energy. When you add up a catalyst to this system, it is going to lower the activation energy so that the reaction can proceed very fast. That is the work of a catalyst. It just lowers the activation energy of every reaction so that the reaction can proceed fast to produce the product. The free energy here basically defines the spontaneous nature of the reaction as to whether the reaction can proceed or not. If the free energy here is negative, the reaction can proceed easily. If it is negative, then it means that the product energy is less than the substrate energy. Hence, their difference as shown here is going to yield a negative value. So when you say a spontaneous reaction, then you make reference to a reaction in which the free energy change of the reaction is negative. A lower energy of the product and a higher energy of the reactant, giving you a negative free energy. Let's look at some energetics of some biochemical reactions in the body. This one is the energy profile diagram for respiration, which occurs in the mitochondria of the human system, in which glucose is being oxidized to produce carbon dioxide and water. For us to form the carbon dioxide and water, there must be bond breaking of the glucose and the oxygen. So glucose must be able to attain some amount of energy that will be enough to break all the bonds in here in order to form the carbon dioxide and water. And that minimum attainable energy for the bond breaking is what we call the activation energy. So as the reaction begins, the reactant becomes charged and increase in energy content till it gets to what we call the transition state, where the molecules, the carbon, hydrogen, and oxygen here are called the activated complex because they can easily fall down to form the carbon dioxide and water. If this reaction occurs without an enzyme, which is a catalyst, it will have a very strong and very high, huge activation energy. Nevertheless, if it occurs in the presence of a catalyst, an enzyme, it will have a very less activation energy, as shown here. So for a respiration to occur, the activation energy is very large without an enzyme, but it is very small with an enzyme. Now the energy changes or the energy lost as heat during the reaction is given as a free energy change, and it is the difference in energies between the product and the reactant which is going to give a negative free energy change. That means that for a respiration to occur in the presence of an enzyme, the reaction is spontaneous because the product energy is less than the substrate energy, and that their difference is going to yield a negative free energy change. That defines the spontaneous nature of respiration in the human body. Thanks for watching. Don't forget to subscribe after watching. Thank you.